popping or on your skin. So understanding that the way deodorant works, deodorant gets into your bloodstream. It's not just stopping BO. So distribution. So act locally or specific sites directly into blood or enters blood through GI tract and then is metabolized by the liver. So in terms of distribution, drug doses, for example, if they're pharmaceutical or over the counter, they are calculated to be broken down by the GI tract and distributed by the liver, and that's why you take this 3 times a day, because if it takes X amount of time to break down the first dose, by the time you take the second dose, the first dose is peaking, the second dose is coming on, and you're maintaining a constant therapeutic level. And it's designed to work like that as long as you aren't drinking alcohol. Okay? Because alcohol essentially interrupts the breakdown of all other drugs to deal with the alcohol. We'll get into that a little bit more. So, it is this distribution, once these drugs are broken down by the liver, their breakdown products are called metabolites, and it's these metabolites that are detected by drug testing. So, metabolism. Liver metabolizes all drugs, so routes change effective doses. So, for example, the beta blocker Inderol, the oral dose is 40 to 160 milligrams. Parenteral, that is an injection, is 1 to 2 milligrams. So, eating cannabis is more effective for pain control than smoking it. There's more to absorb. Takes longer and slower to absorb it that way, orally, so it's more effective for pain rather than smoking your way to pain control. And then excretion. After breakdown by the liver, basically a drug is excreted in the urine, feces, and skin, and respiration. So, all DNA-based forms of life, from the smallest bacteria or virus, algae, poppy, marijuana, Douglas fir, to the whales, use chemicals to communicate between cells. Plants, not being able to move, communicate and defend themselves using chemicals. For example, these are called allelochemicals, and animals will know this and eat certain plants. So, as an example, African bird pepper, or actually all hot peppers, basically create a chemical that's a defense against mammals, and it only works for mammals. Hot actually isn't on your tongue. The taste hot, there's no taste for it on your tongue, there's no hot pain receptors. What it is actually a chemical burn from the plant. And the plant defending itself against being eaten by mammals, and it wards animals away. The idea is that birds will eat the fruit, and birds are unaffected by the chemical, and so they spread it, right? But us monkeys, we just cultivate habanero peppers and gobble them, right? And then we have a corresponding endorphin rush. So those of us who are habanero addicts, that's why we roll. That's the way we roll, okay? So at best, this is good nutrition. At worst, it could be addiction. So this is your brain. There's no frying pan coming up. Nice. You have 2 hemispheres, right and left. The left side of the brain controls the right side of the body, and vice versa. The central nervous system is the brain and spinal cord. So an individual nerve cell is called a neuron. Neuro from the Latin, I believe, nerve. So there are billions of neurons packed in your head without touching each other. What's not shown in this particular graphic is just essentially showing the 2 individual nerve cells and their relationship. The dendrites are like, they're coming into the central body, the soma, which contains the nucleus, and the axon, which is going out from the cell body to touch another cell, but they don't actually touch. What you don't see in here is what's called glial cells, and glial cells are like a smart glue. They basically act as a matrix which can transmit some information, but the idea is and we'll see this in a succeeding graphic, you have, for example, 100 billion neurons in your brain. They don't touch. And you can have 200 different connections from a single cell all around them. So, where they don't touch and there's a gap, the gap is referred to as a synapse. And the synapse is a tiny gap between neurons. The nerve impulse is electrochemical. It's technically a wave of depolarization along the membrane of the cell out here. So it's electrical as it's moving down the axon to the synapse. And at the synapse, what happens? So electro part is a wave of depolarization down the axon, which ends in a terminal. Then a neurotransmitter is released into the synapse. So one of 75 or 80 that we've identified so far. Question, monsieur?
I'm good.
Okay.
I'm trying to figure out the term.
Neurotransmitters received by dendrite, which then depolarizes, sending the message down to the soma, which then retransmits the impulse to the next cell or cells, up to 200 all at once on one neuron.
Now I have a question.
Okay.
Does it send both exactly at the same moment, chemicals and electricity?
So, all right. Here's why maintaining potassium and sodium is really important for your neurochemical health. Okay? That's supposed to be a plus. This is a minus. These are ions. They're atoms that are charged. Okay? They're in balance. Okay? In normal transmission. So there's a wave of depolarization in which sodium and potassium ions are exchanged across this barrier, and that happens in a wave down the barrier, like in milliseconds, in thousandths of a second. Yeah. Right? Then, when it reaches here, somehow, in a process, because remember, this is happening more or less instantaneously at speeds that we don't necessarily comprehend. Okay? All we can see is the before and after. Okay? So one of 80 neurotransmitters is released here. Okay? And into the synapse. And then here's another one that receives the signal, depolarizes and sends the message to the next neuron.
Okay, so it's a charged particle.
Yeah. So it's a wave of depolarization, there's not a spark. Okay. Now, one of the things that also happens that we've, just trying to figure out is that not every impulse is transmitted. So the decision to make to whether it's going to be transmitted on is either happening in the cell body or, right,
What about reuptake?
Right, we'll get to that.
I was trying to figure out if when it leaves, is it a charged particle?
No, not a charged particle. Wave of depolarization.
Okay.
Right. And this basically is breaking it down even farther within the cell. Okay, tiny gap. So cells in your the old theory was cells in your nervous system the reason the term neurotransmitter was created was it used to be thought that it was only cells in your nervous system that did that. And hence the word neurochemicals and neurohormones. And then the idea was to communicate with the rest of the body, they use neurohormones. Well, we found out that there are a bunch of cells that use this system, like white blood cells, to orchestrate. So when I was talking about that term that I threw out, psychoneuroimmunology, it was found out that white blood cells also use this system to coordinate an immune system response. So that's why if you're healthy, and you stay healthy, your immune system response is up. When you're not, it depresses. And also in the presence of certain drug substances, like marijuana does suppress an immune system response somewhat. It's not just you getting stoned, your white blood cells are getting stoned too, becoming less efficient. So neurohormones, while controlled by the nervous system, also produce other cells. Ductless glands, white blood cells, to name a few, as well as target organs. So as an example, when they start studying this, and I don't know if you can see this graphic, how well you can see this graphic, but this is a lab in UC San Diego, which is basically looking at acetylcholine transmission, one of the particular neurotransmitters, presynaptic terminal of one cell, postsynaptic terminal at another cell. There's an acetylcholine receptor, there's neurexin, neuroligin, acetylcholinesterase. So your question about uptake. So anything with an ACE is an enzyme, like Pac-Man. Okay, so acetylcholine, once it's released into the synapse, there's an enzyme, acetylcholinesterase, which turns it off, which eats it up. That's one way. Another way is the neurotransmitter is also taken back into the cell. That's reuptake. So as an example, in scientific English, our laboratory is interested in the structure and function of enzymes and receptors involved in neurotransmission. In particular, we have been studying functional coupling of receptors to cellular responses, specificity of ligand recognition by acetylcholine receptors and acetylcholinesterase, and the structure of cholinesterases and nicotinic acetylcholine receptors. Second area of investigation involves the regulation of expression of the genes encoding these proteins during differentiation and synaptogenesis in neurons and skeletal muscle. So the research is in two parts. One, looking at how this particular neurotransmitter and its the enzyme that turns it off works, and the structure of those different cholines. So cholines all work on skeletal muscle, that is muscle you have conscious control over. Okay? They're all neurotransmission involved in movement. So secondary is, where's this coming from? Like differentiation is basically, when the sperm and ovum met, two cells become one and they start dividing. What's going to be a skeletal muscle? What's going to be a brain? What's going to, so where is this coming from? And is it affected by if mom smokes? That's another one, right? So, and this is actually pretty old, but by pretty old, say 15 years. But if you want to get into this stuff, there is like N tons of NIDA sites and other sites that you can look at where you can find out the trends, because they're always doing studies, lots of things with rats and humans as well. So serotonin transmission, as an example. Think of neurochemicals as the vocabulary of your cells. Each neurotransmitter is like a word. And the same word can mean different things depending on where or how it's used. So some neurotransmitters do double or even multiple duty, depending on what the circumstances are, who's using it when, what the site of transmission is, what the organ system is, all kinds of different things. Okay, after the word is given, it's either eaten by an enzyme, just like acetylcholinesterase, or brought back into the cell in a process called reuptake. So So SSRIs, serum serotonin reuptake inhibitors, are drugs that affect serotonin levels. So serotonin regulates body temperature, sexual response, general arousal, and the amount of sensory data that you're picking up. So we've also mentioned, or maybe you haven't mentioned, but it has been mentioned, SSNRIs, things like Cymbalta, Effexor. These are serum serotonin norepinephrine reuptake inhibitors, which are antidepressants. So here's what happens with a reuptake inhibitor. It creates more of the specific chemical within the synapse, that's the effect, to raise the level of the synapse. So the way they explain this to civilians is they'll say, oh, we are correcting a chemical imbalance. We're saying that your depression is caused by having too low a level of serotonin in your system. So here's a drug that will raise that level and get rid of your depression, or the voices in your head that you have, or whatever. So as an example, let's say somebody's bipolar. All right, I'm supposed to stay in the light for the cams. Let's say this line is normal, okay, whatever that is, and that this is a sine wave. You go up and you go down. And you're above the line, you're in your manic phase, and you're below the line, you're in your depressive phase, right? So one client described taking Effexor, actually Prozac, SSRI, and essentially what it did was erase the down. I mean, he still experienced downs sometimes, but most of the time he was up without being manic. And that was useful for functioning for the particular rough patch that he was going through. But he also noticed that he was a writer, and so it had eliminated his writing voice. Right? Because he liked to, some of the depressive stuff is like, okay, you got to bring that stuff up, cathartic. He had eliminated his writing voice. Prozac eliminated his writing voice, but okay, I'm not suicidal now. Okay, so there's trade-offs, and he noticed the sexual side effects and all the other kind of stuff. And he also noticed, wow, I'm kind of numb, actually. I'm not feeling. I'm not manic, but I'm not feeling. But I am functional. Okay. And for him, Effexor, because then that's another, he was, diagnosed bipolar and also, suffering from depression. So sometimes they gave him Effexor. So when you add basically a norepinephrine reuptake inhibitor, you're increasing norepinephrine, so he felt that was too speedy for him. And yeah, he wasn't depressed, but now he was too speedy. So he liked Prozac for the time that he was on Prozac. Now, one of the things that happens with these particular drugs is certainly there's a risk and a benefit with them. Some people on Prozac will be suicidal. Some not. All right. So if you artificially modify serotonin response in the body, you produce so understand what a side effect is. A side effect is a marketing term by the pharmaceutical company. There's no such thing as side effects. All drugs have effects. A side effect is just a normal effect of the drug that you can't make money from. That in a drug ad, because in a drug ad, they're legally required to mention all those side effects, but you notice how they do that. Right? So side effects, unintended consequences, sexual side effects, increased tendency towards suicide, et cetera, et cetera. So side effect, marketing term for natural effect of the drug in the body affecting systems other than the one you're dosing for. Okay, so you have to assess with your practitioner, your healthcare practitioner, the risks and benefits of therapy, and it helps. And this is where we in our field come in, being able to read the physician's desk reference and translate between scientific English into street and back. Yeah, go ahead.
I don't necessarily know the science behind how a person can stay in a depressed state.
Yeah.
But we can't stay in a, like a happy or just not necessarily emotional state. How the body keeps you down, or your neurons, your anything, your serotonin levels keeps you down.
Yeah, if it is the body that's keeping you down.
Yeah.
It might be the environment, it might be a number of things. Yeah, that's all. I think that's one of those eternal questions. How come we can't stay in a happy, ecstatic state all the time? Well, there are people that try that, but it usually tends to be...
Aren't there people that can stay in a manic state when they're manic depressive for months?
They could.
Okay.
They could. Have you seen I see you. Have you seen the show on Showtime, Homeland?
Yes, I love that show.
Okay, so when Carrie's in a manic state, she's amazing, intelligent. I mean, there are people like that in the real world, okay, that are going to stay focused. That can be useful. Yeah.
There are people who stay happy, not quite manic, but just above normal,
Mm-hmm.
but they don't seek treatment.
Yeah.
So there's no studies on them.
Right. Right.
You can't make
Yeah.
money off of those people.
Yeah. Yeah. There are. And it depends on what you consider normal and what's happy, what's not. I mean, there are people that do that.
So how would you increase both serotonin and dopamine?
And dopamine?
Yeah, like more naturally, not like with methamphetamine or anything.
Let's see. Serotonin and dopamine can be increased with. You didn't take the last class, right?
No.
No. Okay. So serotonin and dopamine can be increased with 3 to 5 minutes of long, deep breathing in a particular rhythm. Naturally. Meditation can do that in as little as 3 to 5 minutes.
Like a yoga class?
Well, yeah, but the pattern goes like this. You have a 5-second inhale and a 10-second exhale for 3 minutes. Minimum. And you can sustain that while awake, too. So there are ways, but, not necessarily taught in medical school.
Isn't there lots of action?
I mean, there are lots of other ways, too,
Yeah.
but, yeah. Playing music will do that, too. Crocheting. There are lots of different ways of doing it. Okay? So there will be side effects of using certain pharmaceuticals. So you have to assess whether are the benefits worth the side effect risk. And so in one of my more infamous sayings, pills are not skills. We cannot ethically argue people off their meds. It's not our place to do that. We can give them a skill set that does what the med does on top of the med. And then if they want to withdraw from the med, they can do that. But the meds are not necessarily a skill set. So this is another graphic produced with your tax dollars that basically talks about dopamine and endorphin receptors and reuptake. These are basically cell membranes. And basically the little graphic of the uptake pump, it doesn't look like that at the cellular level. It's just for illustration. So bringing in dopamine back into the cell after it's been released into the synapse. And an opiate receptor is not technically an opiate receptor. It's an endorphin receptor. Endorphin is the endogenous, that is endo, which means within, endogenous, coming from within, having the quality of coming from within. Endorphin is the endogenous chemical that opiates work off of. Basically looking at the emotional response to pain. So it's one of them, one of the endogenous chemicals that does that. So, neurochemical words. So I'm just going to give you 10 of them out of the 75 or 80. Serotonin, which basically deals with arousal, data flow, body temperature, and sleep. Dopamine, pleasure, memory formation, and brain reward. The brain reward system. Endorphin, emotional pain relief without blocking pain signal, and orgasm. Norepinephrine, the fight or flight response. Norepinephrine is a chemical cousin to adrenaline. In England, it's called noradrenaline, too. But here we call it norepinephrine. Same thing. Acetylcholine, the inhibitory and excitatory, that is, inhibit, calm down, cool down, and excitatory, stimulating. It's a neurotransmitter that does both with separate parts of the nervous system simultaneously. And you'll see how that works when I name the drug. But you already guessed because it was nicotine from the previous slide. Anandamide, pain, coordination, memory, and general sensation. Phenylethylamine, when you're falling in love, that butterflies in the stomach feeling, it's caused by that particular hormone. Beta-phenylethylamine. Testosterone, sex characteristics in both sexes, as well as estrogen. So we all make both. They react differently in our different genomes. Our different gender expressions, and GABA, which is general arousal. All right, so 10, yeah. No?
Is
Yeah, go ahead.
anandamide the one where it shares the receptor for pot?
Yeah, it is. It was discovered in 91. We'll get to that. You anticipated the next slide. All right, so serotonin, LSD, psilocybin mushrooms, SSRIs, Prozac, Paxil, etc. LSD is essentially the opposite of Prozac. LSD competes with serotonin for receptor sites. Serotonin, I ain't explained this yet, have I? How acid works? Are you experienced? Oh, okay. Have you?
Ecstasy also go with that?
Ecstasy is actually the norepinephrine pathway. We'll get to that. Okay. Just to explain. Remember, you have 100 billion neurons in your head. up to 200 different connections all at once with each neuron. Think of the message traffic. If you could put it into words. So when we're teaching meditation, one of the things we're teaching beginning people is understand what's going on in your head already. If you could put it into words, the message traffic alone is like 5,000 words a second. And you could wait, 100 billion, you know what that number is, and 5,000 words a second is like conservative. Right? So not all of it is in words, right? So the itch in your back, you don't put that into words, but it's a sensation, right? Hearing the fan buzz, right, in the air conditioning, the 60 cycle hum of the lights. So all these things I'm calling your attention to and you pick up on, but where were they before I called your attention to them? They're being screened out by serotonin, among other things.
Subconscious.
Yeah, well, we call it subconscious, but something is picking up on it all the time. So serotonin, among other things, and what we call consensus reality, like this, okay? There's nothing in the air between you and I. Don't think about pink elephants. Stop thinking about pink elephants. Okay, so now there's pink elephants in your head, right? But you don't see them out in the room. It's serotonin that allows you to have a subject-object relationship with, okay, you don't see your thoughts out in the world. You don't see them, right? And serotonin that screens out all that signal so that you can focus on specific things. Right? LSD competes with serotonin, so what happens, you decrease serotonin, more signal comes in. So your mind attempts to slot the incoming signal into patterns it understands. So whether you're experienced or not, people on acid have experienced, the room is breathing. Well, it's not the room. It's not the room that's breathing. It's you have screened out the sense of your own body and breathing. And you're transposing that on the room. I say don't think on pink elephants, and acid allows you to see what's in your head out there. Because the subject-object, so it could be fun, it could be disturbing, depending on lots of different things, right? Yeah, emotional state, set and setting, that's part of the rule. So, when doing therapy with folks, asking about their psychedelic trip, how was it? Was it traumatic? Was it not traumatic? Because what you want to look for with psychedelic drugs in particular is the whole issue is set and setting. So set is your mind and emotional set, and setting is your physical setting. I'm not recommending this, but understand it's probably better to trip at the beach than in the middle of a city. Because the drug is increasing signal, and if you can't handle the signal, it's better to be in a natural environment. I'm not suggesting you do that, but you can understand where people's bad trips could come from. Especially if you have some psychological or emotional trauma that has been buried for a reason, and then the drug amplifies everything. So LSD would be like if normal waking consciousness, like on a volume level, if you remember an old analog stereo, where maybe it gets to 1 or 2, LSD is like turning up to 10. Actually up to 100, but your stereo doesn't usually do that. That can be very intense and traumatizing for folks, particularly if they're doing it in combination with other things, right? So it could also be therapeutic, depending if you were doing this in a controlled setting with a guide, et cetera, which is one of the uses of LSD in terms of terminal cancer patients, people who have, okay, let's put you through an experience where you're having a guided experience of your death. So you get used to your death and you have a lowered trauma around your death, which would be useful if you have terminal cancer for people who live in cultures that don't talk about their death. And they're scared. So how do you take them through that experience without having to go through that experience? Well, psychedelic is one of them, and that was one of the legitimate uses of this particular drug, among other things. All right, so set and setting. So, like, screening out, so some of the things that you're experiencing on LSD are not a hallucination in the sense that they're not there. They've been screened out. So one of the famous effects about trailers, like why am I doing this? The way your visual cortex processes information is in milliseconds. So you're actually taking pictures of thousandths of a second on LSD. You see each one of those moments enhanced with a rainbow. Wow. Look at my hand. Ooh. Okay? Like that. That's why people do that. Right? LSD is one of the most powerful, other than certain war gases that do this. Mushrooms, okay, are not as potent, but still as psychedelic. So, to run through this, dopamine, cocaine, endorphin, opium, morphine, heroin, Demerol, fentanyl, norepinephrine, methamphetamine, ecstasy, mescaline, Effexor. So when you're talking about, what was it? Ecstasy, right. It's a norepinephrine psychedelic. Ecstasy is kind of like a combination of mescaline, which is a natural occurring drug substance in peyote, and methamphetamine. So you get like almost psychedelic feel, but you're stimulated. You just love everybody. Yeah.
Isn't that what the chemical structure actually is?
Yes. Right. It's like
One molecule off meth.
yeah, one molecule off meth. Right.
It's the molecule of
Yeah.
mescaline.
Yeah. Yeah.
Would
Right.
it have the same addictive properties?
Mescaline is not addictive according to our science. But, how many people are willing to eat cactuses that make you throw up? That's part of the
In my
trip.
addiction, I found it very addictive. Ecstasy.
Yeah, in terms of the tolerance and withdrawal piece. Yeah, people can't, I'm not saying that people wouldn't want to repeat the experience. I'm saying that in terms of that definition, tolerance and withdrawal, they're not finding it. Unless, of course, when you synthesize it, it's a whole other animal.
So how does ecstasy affect your serotonin?
It's like a methamphetamine. You're on, it kind of exhausts you.
Does it drain it?
Yeah,
Okay.
yeah. Acetylcholine, nicotine, anandamide in marijuana and chocolate, phenylethylamine, the butterflies in stomach, another drug substance in chocolate, testosterone and anabolic steroids, estrogen, people don't necessarily abuse estrogen, but GABA, basically alcohol, GHB, volatile inhalants work along that pathway. GABA pathways, gabapentin is a drug used for bipolar and depression. GABA pathways are like the most numerous within the brain. Alcohol kind of slots into them because it's a fairly simple chemical, like an inverted sugar. Yeah.
Is this where Klonopin?
Klonopin's a benzo, so it works along that pathway too. Yeah. So as an example, so cannabis does not make THC to get you high. It's not all about us. What it does, it makes cannabinoids as a defense against fungus and mold in tropical areas. So for example, the molecule on the left is the natural chemical in the brain, anandamide, and on the right is THC. So you can see it kind of resembles it, but it's not an exact match. And since THC wasn't designed to slot in your cellular receptor sites and is in fact a bigger molecule, it renders the cell membrane around the receptor sites unable to take in nutrients. And if you do that enough, it reduces the efficiency of the cell by 30%. If this is a stomach acid cell, that's probably not much of an issue. If it's a white blood cell coordinating immune response, then it's going to ignore bacteria and viruses around it because it's too stoned to do that. Which is why when you withdraw from marijuana, you get an immune system rebound. All of a sudden you get a cold inside of a week or two. And besides the other things that we'll describe when we get into the THC quit kit. All right, so particularly the plant seeks to protect leaves, flowers, and seeds, and using the cannabinoids, that's why so THC resembles that neurotransmitter anandamide, and that's why leaves, seeds, and flowers concentrate THC, and that's why when we started growing sensimilla, it's to concentrate THC in the flower tops before it goes to seed. And we used to smoke leaf, okay, before sensimilla technology. So the rest of this will be up, and we'll continue this and more next Tuesday.